Hi, my name is Matthew. Welcome to Track 1 Secure Relative Detection. We are from TuneInsight, Broad Institute, MIT, and Yale. In this challenge, the client holds 400 query samples and wants to know for each sample whether there exist some relatives in a test database of size 2000. All data are represented by their genotypes, and they are kept by different parties, so they will have to be encrypted homomorphically and sent to a third party for computation. The third party, upon receiving the 2,400 samples, will homomorphically decide whether to upload a low score or a high score depending on if there is relative in the database. Existing methods for estimating relatedness roughly can be classified as follows. The distance-based estimators compute some distances based on their allele count vectors and then compare them with some threshold to determine whether the samples are highly related. The most widely used King robust estimator falls into this category. The second method, called string matching-based methods, actually takes in phase haplotypes data from some efficient string matching algorithms to try to identify identity by descent regions. If there's a higher amount of identity by descent regions, then they will call the samples to be related. So we first try implementing the King estimator with simplicity attracts us. However, the cost is pretty large because there are a lot of those computations. And for each of the 400 queries, we still need to find the maximum among the 2,000 kinship estimators. And our implementation shows that it will take more than 20 minutes to finish. So we adapt the Homer et al. Approach instead. Their main idea is that we can compute the difference between two distances. The first distance is the individual's genotype and the background population frequency. And the second difference is the individual's genotype and the actual database allele frequency. If this quantity is positive very often, it would mean that the individual is closer to the database than to the population, which means that there is likely to be a relative. And the question it would be, how can we compute similar statistics under homomorphic encryption, and what background populations would be useful?
Hi, I'm Ricky from the Broad Institute, and I'll be presenting the next section. Taking a closer look at the algorithm in the paper, we focus on this statistic. Here, the pop sub j is created using the query database by taking the average value of the variant dosages at that locus across all the samples. The m sub j values are computed similarly using the tested dataset. In the paper, they look at this quantity and perform a transform to model its expected value as a t-statistic. For us to make it easier to use HE, we replace the absolute values with squares and just take the sum of these values over all the sites indexed by j. After seeing this is successful in separating the query samples with or without relatives in the tested dataset, we check how robust the algorithm is and then try to strengthen it. We started by investigating how changing the absolute values to squares would affect the performance of the statistic. And here we have histograms of the values over all the different samples and colored the samples based on whether they had a relative in the reference database or not. And here we see that the version with the squares does just as well at distinguishing between the two groups. So we ended up sticking with that from now on. We then investigated how robust the algorithm was to different types of population structures in the query database. Here we took one individual from the query database who had a relative in the test database and added a number of copies of them to the query database to see how this population structure might affect the algorithm. And we see that it's still quite robust at separating between the two, even in this extreme example here. After a few similar experiments in this vein, we found only one concerning edge case when we had a few query samples where we added a few copies of them and they didn't have any relatives in the tested database. Here we see the algorithm sort of starts to break down from being able to perfectly separate those query samples with or without relatives in the tested database. To try to protect against this type of edge case, we wanted to remove the dependence on using the query database means to compute the pop sub j in our statistics. Instead, we tried partitioning the test dataset into n pieces and using the average dosages over those to create now n values of the pop sub j statistics, which lead to n values for these d statistics for each sample. And then we could aggregate these over the different n to get a final d-statistic for each sample to see if this would help disambiguate between those with relatives and those without. Unfortunately, this strategy didn't seem to be very useful. Here we tried taking the variance over the different d-statistics, and it was not successful in separating between the different categories. In the end, both of our solutions end up using this statistic heavily. They differ in how we compute this pop sub j value. In the first, if we assume reasonable population structure in the query database, we can compute it in the way that was described first by just taking the average dosages across each row in the query database. In the second, we end up assuming that the provided example data is representative of the background population, and we pre-compute the average dosages after removing relatives from that database, and then encrypt these for use in the test set.
Hi everyone, my name is Jean-Philippe Bossua, and I will be taking over to talk about the implementation of our solution. We implemented our solution with a Latigo library and used the CKK scheme. As you can see, we were able to use very small parameters, as only one prime was required to evaluate our solution circuit. There is also a twist. We instantiated the CKK scheme over the conjugate invariant ring, and we'll give additional details about it in a few moments. But before that, a few words about the security of our parameters. We checked their security using Martins-Albrecht lattice estimator, and it turned out that the results were quite high, with an estimated security of about 2 to the 40 ring operations. Very good news, which puts us well above the security target of 128 bits. I will now introduce the conjugate invariant CKKS. This is a work that was published in 2018, and it seems it still hasn't caught the eyes of many. The goal of Kim and Song was to address the fact that in most applications, half the slots are wasted, because they do not need to make use of the imaginary part, and this imaginary part also tends to blow up during large depth computations requiring frequent cleaning. To do so, they observed that the encoding of a pure real vector maps to a closed subring, and that this subring has redundancy in its representation. Technically, we are still encoding only n over 2 reals on n coefficients, but only half of these coefficients are sufficient to uniquely identify an element of this subring. This enables an efficient implementation, which is twice as fast as the one with a non-zero imaginary part. The circuit we want to evaluate under encryption is the sum of the square difference of two vectors of size about 2 to the 16. Written like this, it requires 3 additions, 2 ciphertext multiplications, and an inner sum. We first rewrite it and simplify it a little bit, reducing the number of additions and ciphertext multiplications, and allowing us to pre-compute the terms that do not depend on the query. As usual, the rules did not allow any pre-processing, including permutations of the SNPs, such as reordering them based on their contribution. Therefore, we simply packed the genomes horizontally, each in batches of 4 ciphertexts. Here is a schematic representation of this homomorphic circuit for a single query. We start with the query vector y, which is encrypted and sent to the server. We assume that the server has pre-computed the mean of its database population and the mean of the reference population, which is a step that can involve or not the client. The server performs the homomorphic operations, which translate to the equation at the bottom of the slide, and sends the result back to the client for decryption. You might see that the inner sum is still missing, and this is what we are going to talk about now. So, how did we get this inner sum for free? We can observe that the first row of the canonical embedding matrix has only ones. This means that in the ring, the first coefficient is always the mean of all the encoded coefficients, which is nothing more than a scaled sum. Additionally, we know that the plaintext space is a closed subring, which means that this property always holds. Therefore, we can get the inner sum for free by skipping the decoding step and just extracting the first coefficient of the ciphertext after the decryption. Here are some performance results that we evaluated locally. Making 400 queries takes about 2 seconds, and the interesting part is that over 97% of the total time is spent on reading the data from the disk and encrypting it. Regarding the accuracy, it might look like 13.5 bits is on the low side, but this is due to the compromise with the cryptographic parameters and implementation that we had to do, because we absolutely wanted to keep the size of the coefficients to one machine word, so 1 prime. However, we believe that 13.5 bits is still more than enough, because the threshold in practice to distinguish if there is or not a relative is about 1 over 32 or 5 bits. Finally, I would like to conclude this part with some thoughts on the scoring function and how it shaped our solution. We initially had multiple implemented solutions, but after comparing them using the scoring function, we quickly realized that it was not even worth it to pursue some of them, even if they were to have perfect accuracy. The reason is that if a solution manages to be fast enough, it will trump any other solution regardless of the accuracy due to the exponential factor in the time. On one hand, this enabled us to easily choose which solution to submit, but on the other hand, this also didn't leave us much choice, which is regrettable. In conclusion, we derived a version of Homer's et al. Approach that is friendly to homomorphic encryption and that can be efficiently evaluated while remaining highly accurate. We were able to achieve this result by leveraging the properties of this CKKS encoding to compute the inner sum of encrypted vectors. The bottleneck of the computation being not the server evaluation, but the file reading and encryption. The setting of this computation was very constrained, and therefore, as a future work, it would be interesting to see how the algorithm can be modified to be robust against structured population in the query database, and evaluate how it would scale to real-world datasets. This is the end of our presentation, and I would like to thank you very much for your attention.